we're going to integrate e to the negative ax squared from negative infinity to infinity, and it's going to be awesome. This is super short. We're going to use polar coordinates. If you want to see a longer version of this, you can check that out. But this is really quick. We're going to set our integral equal to I, and then we're going to rewrite the integral in terms of x rather than I. That doesn't change anything. It's the same integral. Now we're going to multiply these two equations together. So the left-hand side becomes I squared. And the right-hand side, with a little bit of rearrangement, multiplying these two integrals together gives us this right here. Now, this is a double integral, but that's okay. Now, we're going to invoke an exponent law where if we're multiplying the bases, we add the exponents, which is what I did right here. And at this point, my friends, we're going to convert to polar coordinates. And I'm not going to go in detail on how to do that, but like really briefly, in polar coordinates, x can go from negative infinity to infinity. So we're anywhere, and same as y. So we're like anywhere, any quadrant on here. So for polar coordinates, r is going to go from 0 to infinity, and theta can go from 0 to 2 pi, so anywhere around here. R squared, using the Pythagorean theorem, equals x squared plus y squared. And so dx dy, converting into polar coordinates, is r dr d theta. R will go from 0 to infinity, and theta will go from 0 to 2 pi. Again, I went in like crazy detail on this, but this is how we get into polar coordinates super quickly. And if we plug that in, then we're going to now integrate d theta from 0 to 2 pi, and we're now integrating e to the negative ar squared. Now we've got to evaluate these integrals, so we'll start with the right one on the right, which is we're going to use a u substitution. We'll set u equal to ax squared, and we'll take the derivative to get du dr equals 2ar. And if we substitute that in, this is what we get. So we still have the integral of d theta, and then this right integral, rather than negative ar squared, we have negative u, because u is ar squared. And r dr, if we rearrange this equation, multiply both sides by dr, divide by 2a, r dr equals du over 2a. Which we got right here. And at this point, we can integrate. Integral of d theta is theta from 0 to 2 pi. The integral of e to the negative u is itself e to the negative u with the negative sign. So here's that negative sign. The 1/2 and the a we yanked out of the integral. And now we're evaluating this at the limits. We have to write the infinity as a limit because infinity is not a number, so we'll just say another variable goes to infinity, and then e to the 0, which is the other limit right here. This limit term becomes 0, and the right-hand term becomes 1. So if we simplify everything, if we cancel the 2's and all that, we get pi over a. These two negative signs cancel right here. See that? We don't care about I squared. We want I, so we'll take the square root. We're left with this choice, plus or minus the square root of pi over a. And we're going to reject the negative sign because our function is always positive. So our area under the curve will be positive. So that gives us our integral in all its glory. And we're done. Hang in there. I know integrals are not easy to learn. You can survive. I've got tons of intervals. Hang in there. Cheers.